Quasi-static magnetization of a magnetic substance. Consider a thermally insulated system consisting of capital N spins, each having a magnetic moment μ0 and located in an applied magnetic field B. The system is initially at some positive absolute temperature T. Suppose that the magnetic field is now very slowly increased to some new value. Give qualitative answers to the following questions. A. What happens to the energy levels of each spin? So, first of all, let me think about what is going on. The magnetic moment for each spin can take values plus or minus μ0, and I'm assuming that B, the applied field, is in the up direction, and therefore the energy corresponding to each configuration of the magnetic moment will be minus mu dot product with B. So I will see that I have two energy levels here for each spin. So I have when mu is equal to minus μ0, I will call this energy level E minus. The energy will be equal to plus μ0 B. So this is when mu is equal to minus μ0. And when the magnetic moment points parallel to the magnetic field, we have the dot product equaling minus μ0 B, and so that would be corresponding to mu is equal to plus μ0. And as you can see, the separation between these two energy levels is delta E equals to 2 μ0 B. So after doing this analysis, so let me note also here delta E is the distance between the high excited state and the ground state, E minus and E plus. So let's answer part A. What happens to the energy levels of each spin? So the energy levels E minus is proportional to B. E minus is equal to μ0 B. So we will see that when B increases, the energy level E minus, the energy value, will increase, and the other energy level E plus is also proportional to B, but it is proportional to minus B. So when B increases, so E plus is equal to minus μ0 B. When B increases, the energy level E minus will increase in absolute value, but becomes more negative. So it's actually numerically it's decreasing. So you can either say in absolute value it's increasing, or you can say the numerical value of the energy is actually decreasing. So the other question is what can happen to the distance between these two energy levels. So delta E is proportional to the magnetic field B, so it's actually equal to 2 μ0 B. So it's going to be increasing. So when B increases, you will see that when B increases, the separation between the energy levels, delta E, also increases. Okay, because the lower energy level is going further down, the higher energy level is going further up, the separation between the energy levels also increases. So that's the answer to part A. Does the mean energy of each spin increase or decrease? The mean energy of each spin, epsilon bar, is given by probability of having a magnetic moment minus mu 0, the energy, corresponding energy is mu 0 b, plus the probability of having a magnetic moment plus mu 0, minus mu 0. So let me see here. So this scenario, E minus, would be, so the corresponding probability I call P minus, this P plus. So mu 0b with probability P minus, and minus mu 0b with probability P plus. So this is going to give us the mean energy of the system. Now, since this is a spin system and I'm talking about the mean energy of one spin, so one spin in thermal contact with capital N minus 1 spins in a thermally insulated configuration, and capital N spins thermally insulated. So I only have a thermal interaction between this one spin and the rest of the spins, which will act as a heat reservoir. So the probabilities actually are given by, I know exactly the form, it's given by the Boltzmann distribution, canonical distribution, C times e to the minus beta mu 0b, plus C times e to the plus beta mu 0b minus mu 0b. So this is the explicit form, and beta is 1 over kT, remember. Explicit form of the mean energy. So we're now changing the magnetic field. So how is that going to affect the mean energy of the system? So the change in the mean energy, the epsilon bar, will be equal to the change in the probabilities times epsilon. So epsilon r dpr plus pr d epsilon r, and this is equal to d bar q plus d bar w. That's first law of thermodynamics. And since we have a thermally insulated total system, basically we will see that the energy levels will change because we're changing an external parameter of the system, but we don't have energy exchange in the form of heat with the surroundings. So d bar q, so this is a scenario where I have d bar q is equal to 0. So I have epsilon r dpr is equal to 0. The probability of occupancy of the energy levels does not change. However, d epsilon r is non-zero. So basically we have some work being done on the spin system because we have a change in the energy levels. Now what happens to the mean energy? So epsilon bar, which is P minus P plus times mu 0 B, as I have written at the beginning. And since the probabilities P minus and P plus are constant, P minus P plus constant, I must have an increase in the mean energy of the system, epsilon bar, is proportional to the magnetic field. But I need to check the value of P minus minus P plus. So P minus corresponds to the scenario where the magnetic moment points anti-parallel to the magnetic field, and P plus corresponds to the scenario where it's parallel. So with no external field, with B equaling to 0, we would have P plus equals P minus equals 1/2. When B is pointing up, we would have the probability of the magnetic moment pointing up greater than the magnetic moment pointing down. So I see that the mean value of the energy of the system minus P plus minus P minus mu 0 B, and P plus is greater than P minus. So actually the mean energy of the system is proportional to minus B. Therefore, so as B increases, the mean energy of each spin decreases. So this is the answer. So the answer to part A was E plus will increase in absolute value, E minus will increase, and the separation will increase. And in part B, the mean energy of each spin decreases. Part C, is the work done on the system in increasing the magnetic field positive or negative? Now, I have d epsilon bar, the mean energy of the system, equals to d bar w. Since I have argued in part B that d epsilon bar should be negative, d bar w should be negative. So what is d bar w? The work done on system A. In fact, it is minus B dot product with mu. So increasing magnetic field B in the up direction, the mu along or parallel to B increases. So the dot product B dot d mu will be positive, but the work done on the system will be negative. So the conclusion is that the work done on the system, because the value is less than 0, by increasing the magnetic field, the work done on the system is negative. Okay. Now let's move on to part D. Now part D, does the mean energy of a spin measured above its ground state energy increase or decrease? So this is again tricky because the ground state energy is also changing. So if you look at my energy levels here, so let me call them these epsilon minus and epsilon plus. Basically, I'm using epsilon because it's the energy per spin instead of E, so it will be better notation. So if I look at the difference between energies, epsilon minus minus epsilon plus, that is 2 mu 0 B. So this increases increases with increasing magnetic field. So we already know this. Now, what is the change in the energy levels? So if I look at the initial situation, initial separation between the energy levels with respect to the ground state energy, so that is initial energy minus the ground state energy, epsilon 0 initial. If I look at its average value, this is the initial energy average value minus the ground state energy. Well, the initial energy average value minus the ground state energy was minus mu 0 b. So this would be equal to initial mean value of the energy plus mu 0 b. Now, what is the final average value of separation between the mean energy and the ground state energy, epsilon 0 final? The mean value. So this would be equal to final mean energy minus the final ground state energy. The final mean energy is epsilon f bar minus, let's call this magnetic field value now minus mu 0 b final. Okay, so this would be equal to final mean energy plus mu 0 b final, and b final is greater than b because we're increasing. So what happened to the mean energy of a system measured above its ground state energy? Did it increase or decrease? So let's look at the difference between these two, delta EF bar minus delta epsilon I bar. So this is going to be the final mean energy minus the initial mean energy of the system plus mu 0 b final minus b. Now the final mean energy and initial mean energy, so these are basically P minus times, so if you remember, epsilon bar was here, so let me recall this equation here, P minus minus P plus mu 0 b. So the same equation applies in the two scenarios I am considering here. So it is P minus minus P plus mu 0 b. It's mu 0 b final in the final configuration minus b in the initial configuration plus mu 0 b final minus b. Now you can see that this is in mu 0 b final minus b parentheses 1 plus p minus minus p plus. So b final is greater than b, so this is going to be positive, and the probability of having the up is greater than probability of having down, so p plus is greater than p minus. However, here I have 1 plus p minus minus p plus. So the p minus and p plus are values that are so they add up to 1 here. So p plus plus p minus is equal to 1. So instead of p plus here or p minus here, I can put 1 minus p plus. So this is going to be mu 0 b final minus b, and then here I have 1 plus 1 minus 2 p plus. So this is going to be 2 mu 0 b final minus b 1 minus p plus. And we know that p plus is less than 1 since p minus is non-zero. So we would have this value also positive. So this is positive, this is positive. So I would find that the mean energy above the ground state actually increases. So delta epsilon f bar is greater than delta epsilon I bar. So the mean energy above the ground state energy increases. Okay. So that's the answer to part D. Now let's look at part E. Does the absolute temperature of the system increase or decrease? Okay, so let's talk about absolute temperature. So I know two things about absolute temperature. So 1 over kT beta is equal to del ln omega del E, where the omega is a function of energy, varies as E bar minus E0 to the power F. So this is the total mean energy about the ground state energy to the power number of degrees of freedom, and this gives us T proportional to E bar minus E0 divided by F, as we did in the previous problem. So since the mean energy above the ground state energy increases, T must increase. So since E bar minus E0 increases, T increases. So this is one way to tell. Alternatively, because I don't have heat exchange, since d bar q is equal to 0, the probability p plus and p minus do not change. And remember that these probabilities, for example, if I consider one of the probabilities, let's take p minus. P minus is c e to the minus beta mu 0 b. So beta mu 0 b must be a constant. So that means mu 0 b divided by kT is a constant. So that means the temperature is mu 0 b over k times a constant. So the temperature must increase in proportion to magnetic field. Therefore, as B increases, temperature also increases. So alternatively, I can reach the same conclusion using the fact that I don't expect to see any change in the probability of occupancy of the energy levels by changing the external parameter of the system. Okay, so we are considering a thermally insulated system consisting of capital N spins. Magnetic moment mu 0. There are two possibilities. Magnetic moment is plus mu 0 parallel to the external magnetic field B, in which case the energy is minus mu 0 b, or it is minus mu 0 and it is anti-parallel to the magnetic field, so that the energy is plus mu 0 b. So that's coming with probability p minus. So these energy levels are in magnitude proportional to B. So when magnetic field increases, the energy levels will shift in such a way that the separation between them will increase. Epsilon minus will go up, epsilon plus will go down. So the energy levels in numerical value, they will be increasing. Does the mean energy of each spin increase or decrease? The mean energy is found by looking at all possibilities of energy values multiplied by their probabilities, and this is a canonical distribution. So here I have the P minus mu 0 b plus P plus minus mu 0 b. That is the energy P minus E minus, and this is P plus E plus. So E plus was minus mu 0 b, right? And the change in the mean energy of the system is epsilon r dpr plus pr d epsilon r over all possible r values. So this is d bar q plus d bar w, and we know that when we have the mean energy, the change in the mean energy of the system due to a heat exchange, this d bar q will not be zero, but if it's due to an external parameter changing, that is work being done, d bar q will be zero. That means the probability of occupancy of the energy levels doesn't change. So epsilon bar is P minus minus P plus mu 0 b, where P plus is greater than P minus because the magnetic field is pointing up. It will be more likely for the magnetic moment to point up. I see that epsilon bar is minus a positive number times mu 0 b. So as b increases, epsilon bar becomes more negative. So the mean energy of each system will be decreasing. Increasing in absolute value, but decreasing in numerical value. So because the epsilon bar is going to be negative, so you can see here d epsilon bar is minus this constant P plus minus P minus mu 0 dB. dB is positive, d epsilon bar is negative. So d bar W from the first law of thermodynamics is negative. The work done on the system is negative. The mean energy above the ground state energy is going to be tricky to analyze because the ground state energy is shifting. Ground state level, lower level energy is shifting down. So I have to consider that. So I find that by this explicit calculation, since the final magnetic field is greater than the initial magnetic field and probability P plus is less than 1, so P1 minus P plus is greater than 0, I have basically an increase in the mean energy above the ground state energy for the system. And because the probabilities are constant, beta mu 0 b must be constant. As b increases, temperature must be increasing in proportion, or you can see that from the number of accessible states that depends on functionally the mean energy above the ground state energy to the power f number of degrees of freedom. We reach our interpretation of absolute temperature. It's the mean energy above ground state energy per degree of freedom, and since the mean energy above the ground state energy is increasing, this is increasing, the temperature must be increasing.